Welcome to this explainer. Today, we're jumping right into something that is absolutely fundamental to our existence, yet, honestly, we almost never notice it's happening. But here's the thing. When we finally do notice it, or worse, when we fundamentally misunderstand it, the consequences can be literally disastrous. We're going to be exploring the non-linear math of life, and as you'll see a little later on, the cities we build. The big core theme we're unpacking today is how assuming life scales up in a simple, straight, linear line is a huge, sometimes fatal, mistake.
So, to understand just how dangerous this assumption can really be, let's start with a question I guarantee you've probably never asked yourself. How much LSD should you give an elephant? Yeah. In the 1960s, researchers working under the CIA's infamous top-secret MK Ultra project actually wanted to know if a heavy dose of LSD might trigger a specific psychological reaction in a totally docile elephant. They got the green light to run this experiment on Tusko, who is an Indian elephant at the Lincoln Park Zoo in Oklahoma. But, well, the researchers hit a bit of a snag. You see, LSD had never been given to an animal anywhere near that big before, so they had to make a mathematical assumption.
The researchers did know the safe dosage for a cat. A 3-kilogram cat can safely process about 0.3 milligrams of LSD. And since Tusko weighed roughly 3,000 kilograms, which is exactly 1,000 times the mass of the cat, the researchers just used simple linear math. They basically figured, hey, just give him 1,000 times the dose, right? Makes sense on paper. So they injected Tusko with nearly 300 milligrams of LSD. Within 5 minutes, Tusko completely collapsed, and tragically he died shortly after. The fatal mistake those researchers made was assuming that safe drug dosage scales linearly with body mass. It absolutely 100% does not. So that begs the question, how does life actually scale?
Section 1. The billion heartbeat mystery. Okay, let's dive into this.
To really wrap our heads around how life handles the math of physical size, let's look at the absolute extremes of the mammal world. On one side, you've got the tiny Etruscan shrew, smallest mammal by mass. It only lives for about a year and a half, but its heart is just racing at an unbelievable 1,200 beats per minute. On the flip side, we have the massive African bush elephant. This giant lives for around 65 years, but its heart beats at this incredibly slow, steady 30 beats per minute. So they are polar opposites, right? One lives super fast and dies young, and the other just takes its time. But if you take their heart rate and multiply it by their lifespan, something honestly magical happens. You get roughly 1 billion. An elephant gets around 1 billion heartbeats in its entire lifetime. And that tiny, frantic little shrew, also exactly 1 billion. A wallaby? 1 billion. A two-toed sloth? Yep, 1 billion. Almost every single mammal on Earth, regardless of where they live or how massive they are, gets roughly 1 billion heartbeats between the day they're born and the day they die. It's wild. But why is this a rule? Well, to figure that out, we have to talk about energy. See, an animal's ability to process compounds, whether that's food or, in Tusko's tragic case, LSD, depends entirely on its metabolic rate, not just its overall bulk. And metabolism generates heat. Way back in 1838, French scientists proposed what they called the surface law. They realized that if an animal scaled up linearly, an elephant would generate 1,000 times the heat of a cat, but it would only have 100 times the skin's surface area to sweat it out. It would literally boil alive from its own internal heat. So they theorized metabolism had to scale to the 2/3 power of mass. Think about it like cooking a Thanksgiving turkey. If you buy a bird that's twice as heavy, you definitely don't cook it for twice as long, right? The heat spreads based on the thickness squared while the volume is cubed. So cooking time scales to the mass to the 2/3 power. For almost a century, biologists just accepted this 2/3 rule as the absolute law of the land. But then, in 1932, a Swiss biologist named Max Kleiber decided to actually put it to the test with some rigorous, hard data. And what he found was huge. The slope wasn't 2/3. Actually, scratch that, it was 3/4. This discovery became known as Kleiber's law. Basically, it means that if you double an animal's mass, its metabolism only goes up by about 68%. It's a massive boost in biological efficiency. And this exact math explains why Tusko died. If those researchers had used Kleiber's 3/4 law, Tusko's correct dose shouldn't have been anywhere near 300 milligrams. It should have been around 53 milligrams.
Section 2. The fractal network of life.
So for decades after that, biologists knew Kleiber's law was a reality, but nobody had a clue why life rigidly followed this exact 3/4 mathematical rule. Fast forward to the 1990s, and we finally get this elegant mathematical solution that literally spans all of nature.
In 1997, 3 researchers, West, Brown, and Enquist, teamed up and cracked the code, creating what we now call WBE theory. They realized the secret was hidden in the geometry of our internal plumbing, things like our circulatory system. They laid out 3 basic premises. 1, these blood networks have to branch out and fill the entire space of the body to reach every single cell. 2, the terminal units, like the tiniest little capillaries feeding an elephant's skin cell, are basically the exact same size as the ones in a tiny mouse. The elephant just has a whole lot more of them. And 3, over millions of years, evolution has perfectly optimized these networks to pump blood with maximum efficiency and minimum wasted energy.
To pull off that kind of perfect evolutionary efficiency, your blood vessels have to branch out in a self-similar fractal pattern. It's kind of like crumpling up a flat, two-dimensional piece of paper in your hands. As you fold it and crush it over and over, that 2D surface mathematically begins to fill up a 3D volume. In the math world, this creates what's called a Hausdorff dimension of exactly 3.0. Using this fractal network, biology effectively packs a frankly enormous amount of metabolic surface area into a confined 3-dimensional body. This is exactly what allows animals to evolve to be so large while remaining incredibly energy efficient. And this brilliantly illustrates why WBE theory was such a game changer. The math didn't just explain Kleiber's 3/4 metabolic law. It accurately predicted dozens of other biological traits across all these crazy exotic exponents. According to the fractal math, heart rate has to scale at a -1/4 power, which just means bigger animals naturally have slower hearts. Meanwhile, lifespan scales at a +1/4 power, meaning bigger animals live longer. And because heart rate and lifespan are perfectly inverted mathematically, when you multiply them together to calculate total lifetime heartbeats, the mass variable just cancels itself out entirely. Poof, gone. You are left with one single universal constant, 1 billion heartbeats. Now, what's really interesting about this slide is that there is one massive, glaring exception to this universal rule. Us, humans. You see, about 3 centuries ago, human beings died pretty much right on schedule with the rest of the mammal kingdom. But thanks to things like germ theory, way better sanitation, and modern medicine, we've completely broken biological limits. The average human today gets nearly 3 billion heartbeats before they die. Through science and technology, we have literally handed ourselves more than a full extra life. And it turns out, the very spaces where we invent that technology, our cities, follow their own fascinating mathematics.
Section 3. When cities act like mammals.
When the physicist Geoffrey West finished mapping out the math of mammals, he actually turned his attention to human-built environments. And astonishingly, he realized the exact same mathematical scaling rules that govern our blood vessels and our metabolism also govern the cities where most of us live. So the really crucial point here is that cities do scale predictably, but they scale in 2 completely different directions at the exact same time. When a city doubles its population, it doesn't actually need double the infrastructure. Things like gas stations, roads, and electrical cables scale sublinearly at about a 0.85 exponent. That is a massive shared economy of scale. You only need about 74% more gas stations for double the people. But socioeconomic factors, things like total wages, GDP, the number of patents filed, and yeah, unfortunately, crime and disease, those scale superlinearly at an exponent of around 1.15. So for every time a city doubles in size, you get roughly 120% more wealth and innovation while actually using less infrastructure per person. Because of this intense clustering of shared resources, wealth, and innovation, cities actually generate this palpable sort of kinetic energy. The overall pace of life systematically accelerates. In fact, researchers have gone out and measured this directly. Pedestrians literally walk faster in larger cities. And it's not just about trying to avoid foot traffic on a crowded sidewalk. It is quite literally the vibe. The superlinear scaling of massive cities genuinely gets people amped up, physically increasing your speed of life.
Section 4. The science is never settled.
Now, it's really easy to look at this constantly accelerating pace and the flawless sweeping math of WBE theory and just assume everything is completely figured out. But the scientific debate regarding biological scaling is actually far from over. There is a lot of pushback. First, let's talk about the anxiety over our accelerating cities. It's so easy to feel like humanity just won't be able to keep up with this superlinear speed forever, but I want you to read this quote. Everything nowadays is ultra. Wealth and rapidity are what the world admires. Young people are stirred up much too early in life. Sounds exactly like someone complaining about social media and modern hustle culture today, right? Well, this was actually written in 1825 by Wolfgang von Goethe.
Life has felt dizzyingly fast to humanity for centuries, and yet generation after generation, we just continue to successfully adapt and reap the benefits of scale.
But what about the biology side of things? Well, researchers like Peter Dodds at the University of Vermont argue that the WBE theory might just be a little bit too perfect. Skeptics are quick to point out that if you look at the raw data for hundreds of different species, it is incredibly noisy and messy. I mean, measuring the true resting metabolic rate of a massive, completely unstressed elephant is notoriously difficult. Some recent analyses even suggest that Kleiber's three-quarters law might not be a universal truth after all. Instead, smaller animals might actually scale closer to that old two-thirds surface law from 1838, while only the larger mammals shift into that three-quarters fractal efficiency mode.
Which ultimately leaves us with a lingering, unsolved mystery right at the heart of biology. From the fatal linear miscalculation with Tusko the elephant, to the 1 billion heartbeats that mysteriously connect a tiny shrew and a giant whale, all the way to the accelerating sidewalks of our largest megacities, it is incredibly clear that life is deeply nonlinear. But the exact exponent that rules our metabolism, that remains fiercely debated. Is it two-thirds, three-quarters, or maybe a shifting curve across the vast, messy tapestry of life? It's a centuries-old question just waiting for the next generation of researchers to finally definitively answer. Thank you so much for joining us on this explainer. Keep questioning the math of the world around you, and we'll see you next time.